This is a churn drill, working on a solid hill of iron ore on the Quebec-Labrador border. It marks the final chapter of a long story, a story covering 4 years of effort, the labor of thousands of men, and the expenditure of $250 million. A story that is the basis of this report on what we had to do to get ore in ore. Start with the land. Lonely, vast, and remote. It's been neglected for centuries. But locked in that lake-studded plateau are tremendous mineral treasures. Getting them out meant breaking down this land's age-old defenses of climate and terrain. It meant breaking through the protecting wall of 100 miles of Laurentian uplands. And it meant fighting and winning the endless war with distance. Only a map can make this clear and thus underline the constant limitations geography imposed. Work started at the old fishing village of Sept-Îles on the north shore of the Gulf of St. Lawrence. Montreal, 484 air miles away. Montjoly on the south shore, the nearest railroad point, 141 air miles away. The ore bodies themselves are north around Knob Lake. Here, a new town site named Schefferville is being built. A 357-mile railway was built from the Gulf of St. Lawrence to the ore bodies. Come back now 4 years to Sept-Îles as we retrace what had to be done to get out ore. The centuries had gone slowly for Sept-Îles, each finding it as the last had left it. A quiet fishing village on the edge of the wilderness. But that changed at the midpoint of this century of destiny, making Sept-Îles the gateway to one of the greatest mining ventures of all time. On October 2nd, 1950, the first bulldozers came ashore from a small St. Lawrence freighter and began knocking down brush back of the old village. They were opening the way for ore in '54. In the dock area, pile drivers started hammering down sheet piling of corrosion-resistant, copper-bearing steel as a fishing village took the first step toward its eventual position as a major seaport, which will ship millions of tons of ore each year. Out in the Gulf of St. Lawrence, a dredge pumped up tremendous quantities of sand and pushed it into the area behind the dock. We were making land here, building a firm base for the modern and massive equipment necessary to load the great vessels that would be calling when enough ore started coming down in '54 to test facilities and train personnel. Sometimes the Gulf can act like a full-fledged ocean, and it severely pounded temporary dock facilities, but never enough to stop the stream of supplies and equipment that came ashore to serve the expanding project. Trucks needed up the line. Tank cars for fuel needed everywhere. Boxcars for supply trains bound up the line. Locomotives for the long haul north. Aggregate for concrete. And it wasn't always springtime in the harbor. Sometimes we sent ashore a load of ice as a bonus. And always heavy equipment for a big, heavy job. A lot of it was put to work preparing the foundations of what was to be the dumper house, the place where ore would eventually be transferred from railroad cars to conveyors which would load waiting ships. Excavation for the foundation extended below the waterline. It was necessary to ring the pit with well points that kept carrying out water as fast as it could seep in. This work, as well as all the rest of the major construction on the project, was done by a combination of 4 contracting firms: Cartier, McNamara, Mannix, and Morrison Knudsen. known colloquially as CMMK. Iron Ore Company of Canada, which built the project, is made up of Hollinger Consolidated Gold Mines Limited, M.A. Hanna Company, and 5 steel companies, Armco, National, Republic, Wheeling, and Youngstown Sheet and Tube. They put up $100 million of the $250 million total cost. The rest will be lent by 19 American and Canadian insurance companies. Over on the Marguerite River, 24 miles away, other construction crews were busy erecting a dam and power project which would supply electricity to operate dock and terminal facilities and to serve the expanding town of Sept-Îles. In a construction project this size, you search for ways to use materials at hand. In this case, local rock was quarried just a few hundred yards from the dam site, hauled to an aggregate plant, crushed, washed, sized, sorted, and thus processed on the spot into aggregate suitable for the high-quality concrete needed for the job. The object of this construction is the eventual completion of a gigantic plug across the gorge of the Marguerite, bottling up all the water in a drainage area 3,500 square miles in extent and creating a lake 53 miles long. Specifically, there will be a dam 517 feet long, 128 feet high, containing 52,000 cubic yards of concrete. It'll be flanked by an earthen dam, 2,680 feet long. This was a project where everything had to be done at once. All the while we were building in Sept-Îles and at Marguerite, we were also pushing north. We were building at all places, in all directions at the same time. Fleets of heavy equipment were ready to push steel ahead, up the line. And as soon as rail was down, we sent trains north over it with yet more equipment for yet more construction, always increasing the tempo of the work. Daily, the trains pulled out of Sept-Îles to supply a construction battle that has few equals in history. The epic struggle to build the Quebec, North Shore, and Labrador Railway north to the ore body. 12 miles north of Sept-Îles, we had to cut a half-mile tunnel through Laurentian rock, and then immediately had to throw a 705-foot bridge across the deep gorge of the Moisey River. The south end of the bridge tied directly into the north portal of the tunnel, and the river is more than 150 feet straight down a sheer cliff. Building in these conditions is akin to pulling yourself up by your own bootstraps. Steel and men inched their way across the chasm on an intricate web of cable. We crossed the Moisey in June 1952, but there was no let-up for the construction crews. On the other side of the bridge, there is rock, mile after mile of it rising in sheer canyon walls. Drill crews sweated their heavy wagon drills up the cliff sides, fighting for every inch, toiling painfully over the bleak face of some of the oldest rock in the world. This was building a railroad the hard way, but there was no easy way to go north for the ore in Quebec, Labrador. Drill bits sank home thousands of times in the stretch between mile 12 and mile 17. In these 5 miles, we blasted down 1 million cubic yards of rock. And we built ourselves a roadbed. 1 million yards of rock and 600 tons of dynamite, and the trains kept moving north over the new rail, rolling toward the head of steel, toward the wilderness we had not yet breached. As soon as we cut new tunnels and laid new rail, northbound trains carried in supplies and equipment to the next stage of the job. Much of the freight they hauled was used to feed and house men working along the line. There were 18 major construction camps. At peak operations, they housed a total of 6,900 men, most of them Canadians coming from Quebec and Newfoundland. And as the rail went north, so did the wires. steel-cored, aluminum-covered wires to tie together the modern centralized traffic control system, which guides the Quebec North Shore and Labrador Railway. There are 14 wooden trestles, built in part of local lumber, to supplement 5 steel bridges on the way north. Drainage was a constant problem. To solve it, we pierced the roadbed with 16.5 miles of culvert, ranging up to 12 feet in size. And nowhere was drainage more troublesome than in the muskeg, which begins north of the Laurentian uplands. A quagmire of rotting vegetation, it stubbornly defies efforts to move it. Luckily, muskeg along the QNS&L was not the bottomless kind found elsewhere in North America. Here it averages 3 to 4 feet thick, and we put fill right over it, expecting it slowly to compress and compact enough to make a stable roadbed. As soon as we had a roadbed, we laid track over it. One shift ahead of the steel, we distributed ties so nothing would slow up the rail-laying crews. Cranes picked up rail from special skeleton cars and swung it into position. Good teamwork made it possible to lay one rail every 60 seconds. When all the rail on a skeleton car had been used, the crane lifted the car off the track, set it aside, and went to work on a fresh car. Then the crane would move forward over the new track and repeat the cycle. But machines alone didn't do the job. It also took tough and able men drawn from every province in Canada, men capable of working 10 and 12 hours a day to accomplish a job without close parallel in construction history. They did it during the winter of 1953 and 54 as we were driving to be ready to move ore. From December into February, they laid track in weather that went down to 50 degrees below zero and colder. This is weather that strains equipment to the utmost. Motors have to be running constantly, for if they freeze, they'll not start again until the next thaw. And some equipment will operate at only 50% efficiency. In December 1953, working out of the railway camp at mile 290, the track laying crews made more than 2 miles a day for 10 straight days. Going into Silver Lake Yards, in the heart of the ore district, they made 9,700 feet on the last day of track laying. The golden spike, symbolizing the end of rail construction to Knob Lake, was driven on February 13, 1954, by Jules R. Timmins, president of Hollinger Consolidated Gold Mines. It was rough, but track laid during that last drive down the home stretch made it possible to move ore in 54. Winter ballasting was even more precedent-shattering than winter track laying. Ballast that should have been frozen as hard as the steel side of a railroad car flowed easily at 40 below zero. Each particle seemed to be locked in its own little ice capsule. We took gravel for the winter operations from a gigantic glacial esker at mile 290. In the spring of 1954, we speeded track racing operations with a ballast sled. Pulled behind a locomotive, it raised track and spread ballast at the rate of 2 to 3 miles an hour, far faster than traditional methods, helping advance serviceable track for ballast trains and mechanical tamping operations. And all up and down the line, we searched constantly for new answers. There are 100 stories to tell about the means used to move men and supplies up the line to the site of construction. Stories about helicopters, which make any region accessible. About the experimental swamp buggy we hoped would solve the problem of muskeg. About the canoes that carried survey teams into the bush. About the beetle-like snowmobiles that were so valuable in the winter. About the fight to keep rail open in the snow season so that supply trains could move north. about the great convoys of 1952 and 1953 that traveled for 10 weeks across the frozen bush and icebound lakes with heavy supplies and equipment for spring work up the line. About the little 44-foot boats we built on the project. They hauled more than 150,000 tons in 1953. But the greatest story of all was the airlift, the story of the Hollinger-Ungava Transport Company. Always overhead there was the sound of a plane, the constant background to the fight for ore. For 3 years, there never was a period of more than 48 hours without a flight. Around the clock and around the calendar, the planes took off. From October 1950 until December 1953, Hollinger-Ungava missed only a total of 11 days, not counting Christmas and New Year's Day. This in a region which is the home of some of the world's worst flying weather. Every man, every machine, every pound of food used up the line had to go at least part of the way by airlift. The airline was based at Montjoly, on the railroad on the south shore of the Gulf of St. Lawrence. 141 miles to the northeast is Sept-Îles, its next port of call. From there, north, 320 air miles to Knob Lake is wilderness. In its 3 years of peak operation, the airline flew nearly 139,000 passengers, 170 million pounds of freight, totaling 15 million ton miles over this country without scratching a crewman or a passenger. The record was made possible by skilled pilots, many of them RCAF veterans, backed by top flight organization, planning, maintenance, and weather information. At the peak, 82 pilots and co-pilots were flying 18 aircraft maintained by 100 mechanics. There were 14 landing strips up the line, many of them just single runways, bulldozed out of the bottom of narrow canyons along the railroad right-of-way. Aircraft were equipped with crosswind landing gear to overcome the handicaps imposed by landing strip locations and the ever-present menace of tricky crosswinds whirling through the deep valleys. Hollinger-Ungava Transport made history in this struggle to get ore. Building Menihek Dam is an example of the sort of job HUT did. Here it flew in almost all materials, including a total of 190,000 bags of cement and 7,000 gallons of gasoline a day. Menihek was a place of heartbreak. We built first a temporary cofferdam and bridge, only to see the spring of 1952 bring an unprecedented breakup and runoff which washed out months of hard work. One major handicap in all construction work was the lack of accurate runoff data in this wilderness area. Here again, we crushed local rock to make aggregate for the 31,000 cubic yards of concrete we needed. But rock around Menihek posed a special problem. It was so full of tannic acid that we had to wash it to turn out a suitable material. Winter is hard in this country, but at least in winter you can stay on top of the ground. Men and machines can move. But the spring runoff, followed by the thawing of several feet of ground frost, produces a thin, hard-to-handle mud. It's hard to move it out of the way, and anything caught in it shows a strong tendency to sink out of sight. This is a land of extremes, and each season brought its own problems to the men who were pushing to get ore. "900,000 cubic yards of earth had to be moved at Menihek, and they were far from being the easiest 900,000 on the project. But the builders persisted, making concrete from acid rock, moving and pouring it winter and summer to raise the face of a 517-foot-long dam, which will also serve as a bridge over the Menihek to carry the railroad north to the ore bodies 30 miles away. Burnt Creek was the first settlement in the ore country, but it's now known to sit on 10 million tons of ore, and will be torn down to make way for the shovels. The first tote roads in the bush fanned out over the hills from Burnt Creek. They led back to drilling teams whose rigs, supported by tripods of native spruce poles, probed the depth and extent of Quebec-Labrador deposits, proving 417 million long tons of direct shipping iron ore. Nearby Knob Lake, named for the promontory in the background, was the site of a seaplane base. The new town of Shefferville will be built on this site. By the spring of 1954, bulldozers were clearing the way for railroad spurs past the ore bodies, spurs which will carry some of the first ore to be shipped south. They tie into the main line of the QN-S&L at Silver Lake Yards, outside Knob Lake. Communications men followed close behind, stringing the wires which will link the whole vast project together. A land lonely and lifeless for centuries has come awake. The roads straggling through the bush do little to change the essential emptiness of the ore country, but they are roads, men do move over them, and the face of a land that has not changed since the last glacier is changing now. A crushing plant and loading pocket rise against a gray-green hill. On one side of the valley, civilization. On the other, the timeless north. The big shovels bite into the thin overburden, seldom more than 7 to 10 feet thick, that lies across the beds of rich ore. This stripping compares with the more than 250 feet necessary on some of the deposits remaining in the Great Lakes Superior Ranges. Once the overburden is removed, shovels will scoop out and load ore in the same way. 20 million tons of ore already stripped lies under this churn drill, which is sinking blasting holes to loosen ore for the shovels. Some of the first ore shipped will come from this deposit. This bench is cut into a solid hill of ore. Huge 6-yard electric shovels, each representing $250,000, will move ponderously down it, dipping their heads to bite into a face of weathered earth that runs nearly 60% iron. This is what we came for. This is why we built 2 towns, 2 power projects, and a railroad. This is ore to feed the free world's blast furnaces, and we're ready for it down the line. Menihek is ready now, an earth and concrete barrier across a chain of northern waters draining 9,000 square miles. It generates 12,000 horsepower and can easily be expanded to twice that. Expansion to 50,000 horsepower is possible with additional construction. And when the spring thaws come from now on, they'll find us ready. They won in 1952, but in 54 and the ore-filled years ahead, the picture will look just a little different. Down at Marguerite, water that for centuries ran wasted to the sea has been dammed and is falling 115 feet to give us the power we need at the terminal area, falling to turn 2 12,500 horsepower generators. We're sending 44,000 volts up the hill and around the bay to Sept-Îles. And when the power reaches Sept-Îles, we're ready for it there too, ready to put it to work. The dock is completed, jutting into 37 feet of water at low tide. Inland, the symmetrical arms of the ore stacker are spread to stockpile reserve ore. The small amount of ore to be handled in 54 will serve to test facilities and train personnel. Regular commercial production of ore is planned to start in 1955. In the background is the dumper house. It can turn over and empty 2 railroad cars, each carrying 85 tons of ore every 65 seconds. A belt conveyor system carries this ore to the 1,000-ton mixing bins, which feed it down another conveyor system along the dock, which loads waiting ships at a peak rate of 8,000 tons an hour. Most of the ore produced in the next few years will probably move by deep water vessels from Sept-Îles to Atlantic coast ports such as Philadelphia and Baltimore. It's 1,366 water miles to Philadelphia, 1,550 water miles to Baltimore. From 2 to 3 million tons a year will be shipped up the St. Lawrence to Montreal. Here it will be transferred to smaller Canadian vessels, which can negotiate present St. Lawrence canals and locks. These ships will carry ore to Ashtabula, Cleveland, and other traditional Great Lakes ore ports. Present Great Lakes carriers will be able to sail directly from Sept-Îles when the St. Lawrence Seaway is completed. It's 952 water miles from Sept-Îles to Ashtabula, only 76 more than from Duluth to Ashtabula. We're ready for ore in 54 and for increasing millions of tons of it when full commercial production gets underway. With the Sept-Îles facilities finished, dredges are at work on the St. Lawrence, 25 miles from Montreal, where we are building a great trans-shipping terminal. It's taken 4 years, $250 million, and thousands of men, but we are bringing out ore in 54.